Some more probability stuff. We will tie this into probability. So the first thing I will do is my little recap. I like to do little recaps because it sets a context, right? This is kind of the overview. It helps you know where you are. And so here's our little recap. We've learned about probability in this class. Actually, I guess I made a video. I didn't teach it to you directly. I used to do that, and now I just use the video. And we found, this is kind of mathy notation on the left and kind of not on the right, that the probability of some event A consists of the number of ways. It's a fraction. It's always a fraction. Probability is a fraction between 0 and 1. It's the number of ways that A can happen divided by the number of ways anything can happen. And so the new thing we are going to learn today, we are going to start learning today, it's a more involved subject and it will take us more than one session, is this number of ways. So how do I love thee? Let me count the ways, right? That's, who is it? Elizabeth Barrett Browning? Portuguese sonnets? I don't know if I really know that. I'm saying that. You'd have to look it up. And this is our big question. How do we count things? Because we can't use this probability formula if we don't know the number of ways something can happen. And it turns out that math comes to the rescue, as it so often does. Of course, I'm prejudiced because I'm a math professor. But there's a branch of math called combinatorics, and it is the branch of mathematics that deals with counting. And I encourage you to learn this word. You might have to put it on a little card, keep it in your pocket and look at it a few times. Combinatorics. It's fun to say. And the reason is you go home, right? Some of you are already home. And they say, so what did the crazy guy do today in class? And you say, oh yeah, we were learning counting. Well, no one's impressed because when they were 4 years old, when they were 5 years old, they learned to count. And so if you say, oh, we're learning counting, yeah. But if you say, oh, we're doing this new branch of mathematics, it's called combinatorics. Well, nobody knows what that is. And so they're really, really impressed. And they'll treat you nicer for a few hours. So this is the idea of combinatorics. Combinatorics as we will do it, right? Because I am not assuming you have any math background at all. I'm not even assuming you know algebra. I'm assuming you have the ability to add, subtract, multiply, and divide using a calculator if necessary. And then everything else I teach you. And so I'm going to teach you some very basic combinatorics. Combinatorics is a subject not only in this Connecting with Ideas class, it's also found in Math 123, which is Math in Modern Society. Some of you will take that. Typically, if you are in some field that doesn't need a lot of math, that's usually the transfer class that you sign up for after completing the prerequisites. And it has a unit on combinatorics. And Math 153, which is statistical reasoning. A lot of our nursing people will take that class, and it has a unit on combinatorics. If you're going into one of the STEM fields, so if you're engineering or accounting, something like that, chemistry, then you're probably taking Math 143 algebra and then calculus. Some of you are in calculus already, right? Because you did a lot of math in high school. And algebra and calculus don't do any combinatorics. More's the pity. If you are really, really interested in combinatorics, and this applies mostly to math majors, there are typically, not at our school, and I'm not even sure if BSU has one. I don't recall. But when I was at Portland State as an undergrad years and years ago, there was a class in combinatorics. That was the whole class, and there was a textbook, and it was this little pink book, I have it somewhere, on combinatorics. And we spent an entire semester, and most of it I did by hand without using a calculator, so it is possible. My knowledge of combinatorics is head and shoulders above a lot of the people in the math department, because I did take that class and it wasn't a requirement for all math majors. It was an elective for math majors, and it sounded interesting to me, so I did it. And not everyone does, and so not everyone's an expert in combinatorics. I myself, having taken a whole semester, am not an expert. I know some of my colleagues at Boise State who are experts in combinatorics. They got their PhD writing a dissertation about a topic of combinatorics, and the things that they do and the mathematical journals that they read to keep up on the topic are so far above me, I have no idea what they mean. So combinatorics, it starts off really simple. We will keep it fairly simple. It is a very important branch of mathematics nowadays because it directly is involved with computer programming and especially machine learning. And machine learning, isn't that what we're trying to hit? We're trying to get to the singularity. We want artificial intelligence. We want the machines to do everything. We want self-driving cars, and you can believe that the people who program self-driving cars are always concerned about what's called combinatoric explosion. There are so many things and the numbers get so big so fast. What is it? We need more computer memory, and you don't have more computer memory, and what you need is a better algorithm. And so they're always trying to solve these combinatorics problems. So I will give you an example. The very most basic thing we can do in combinatorics. There's this thing, and it depends actually on which class you take here at CWI or wherever you end up. If you take the Math 123 class, this is called the Fundamental Principle of Counting. And if you take the Math 153 Statistics class, it's the multiplication counting principle. And 123 calls it the fundamental principle of counting. It is fundamental. I like things that are fundamental because they have fun in them. See, we're already having fun. Isn't this fun? But it also is a multiplicative rule. There's multiplication in it. And so I kind of like the way the stats book does it. But I have to call it something, and different books call it different things. I'm calling it the fundamental principle of counting. If an event, here it comes, if an event can occur in m ways, and m here, it's a number, 3 ways or 7 ways or 1,000 ways or 12 ways, whatever it is. And a subsequent event can occur in n ways, and here n, it's another number. So we're just using some variables, some algebraic variables to make this general. Then, here comes the then, that's our if. Then, the sequence of events can occur in, and here's the multiplicative part of the rule, m times n ways. And if you're very, very new in math, you might not know that this little dot means multiplication. So something can happen m ways and something else can happen in n ways, then the combination, right, you're seeing where the word combinatorics comes from. The sequence of events, the first event and then the second event, can happen in how many ways? Just multiply the individual values, m times n. So let me give you an example. Example. Fred has 3 shirts. That's the first event. Fred has 3 different shirts. Gosh, that's not a lot of shirts. And 2 neckties. That's the second event. How many ways can Fred have a necktie? 2. And I say this is a made-up example because I'm sure that Fred does not own any neckties. I've seen the way Fred dresses. Here's our question then. How many ways? And whenever you see a question that starts how many ways, then you know you're dealing with combinatorics. How many ways can Fred get dressed? How many outfits does he have? Right, he's trying to look good for a job interview or a date. I don't know, his wife wouldn't like that. What do you mean date? Well, maybe it's date night with his wife. I'm hoping Fred isn't fooling around on the side. He wouldn't be successful at it. I mean, I've seen Fred. Okay, so how do you do it? Well, the first event is 3 shirts. And we use the multiplication rule, the fundamental principle of counting. He has the second event, the subsequent event is 2 neckties. And you multiply 3 times 2, and you find that Fred has 6 different outfits. And this assumes certain things, right? It assumes that the ties actually go with the shirts. It's very possible that some of these outfits would be awful, awful things, and you wouldn't want to wear them. I don't know if that would stop Fred. But he has 6 different outfits. And then what? You can start doing probability with it. Well, what's the probability that Fred's going to wear, because it's dark, he gets up early in the morning and he's trying to put on this outfit and he doesn't want to wake his wife. So he doesn't turn the light on. He just reaches in the closet and grabs one of the 3 shirts, and it's dark, so he doesn't know. It's at random, totally random. And then he opens the drawer and pulls out his tie, and he doesn't know which one it is because his wife put the ties away, and it's totally at random. What's the probability that he's wearing the blue shirt and the black paisley tie, right? And you say to yourself, well, how many ways can he wear the blue shirt with the black paisley tie? Well, there's one way, the blue shirt with the black paisley tie. And then how many different ways could he get dressed? And that's what we just found using this principle of combinatorics. There are 6 ways. And so what's the likelihood that Fred is wearing his shirt with the blue paisley tie? Is that what I said, or was it a blue shirt? A blue shirt with the black paisley tie. Whatever it is, I'm making it up as I go. What's the probability he's wearing this particular outfit? And you would say it was 1/6. It's the fraction 1 divided by 6. And you could turn it into a decimal or a percent if you wanted to. We learned that in the video. So let's do some new stuff. Here comes Fred again. Fred is in charge of the talent show at his club. This is probably a mistake. I'm not sure that Fred has the talent to run a talent show, but no one else wanted to do it. There are 5 performers, 5 different acts. There's a lady that sings, and there's a guy who tells jokes, and then there's a little girl with some dogs, and yeah, that kind of stuff. How many ways can Fred arrange order of these 5 acts? And here, arrange and order are important, and we will see as we learn more about combinatorics that one of the big questions we will always have is, does order matter? And if order matters, well, it's different than if order doesn't matter. So here order matters. And why does order matter? Well, because in any show, I mean, the order really, really does matter. If you've ever been in a talent show, or if you've watched a talent show, or if you've, like Fred, been in charge of organizing a talent show, you have to start with something that pulls the audience in, right? You want a pretty good act. You don't want one of your, people, the lady's singing and she's been a member of the club for so long. We have to put her on. I mean, nobody likes the singing, but we have to do it because, well, don't put her first because nobody likes it, and it's going to deaden the whole thing. Comedians, they want a warm up. They want people in a good mood when the comedian comes out, and so you can't have the person reciting Edgar Allan Poe's Raven. Yeah, would that be a talent? I guess it is. Someone could do it. But it's kind of a downer, it's sad at the end. And then comes the comedian, and you're supposed to laugh at his tales of his of his family. And no, this doesn't work. So order definitely matters. And no one wants to come on after the little girl with the dog, because in comparison, it feels like, yeah, this isn't very good. The little girl with the dog is always so charming. So here, the order does matter. We could even emphasize this. We'll write it down. Order matters. So what are we going to do? We're going to use this fundamental principle of counting. And we'll think, well, how many ways can we order the very first act? How many ways can we choose it? And then how many ways can we choose the second act and the third act and so on? And so we'll create these 5 slots, set it up with 5 slots, one for each time slot. That's why it's a slot, right? One for each time slot. So the first act, the first performance, and then the second performance. You won't write them out like this every time. Once you understand the principle, then you'll just use the math equation. And it's a very simple equation. In this class, we do it with a calculator. You have to add, subtract, multiply, divide. Guess what? Here we are multiplying. So this fundamental principle, sometimes it's called the multiplication principle in the 153 class. So the question is, how many ways can Fred choose the first act? And you say, well, there's 5 performers, right? Yeah, well, then there's 5 acts. Okay, so he could choose 5. And then who comes on next? How many can he pick from? Well, one person already performed, and so there's 4 left. And then here comes the third act, and how many ways can he choose? Well, 2 of them are done, and so I guess there's 3 left, and then there's 2 left, and then at the end he doesn't have much of a choice. It better be the person that's left. Okay, you dancers, you're going on last. Okay, yeah, because the dancers are the only ones that are left. And then what do? We're going to multiply. This is the multiplication principle. And so we multiply this way, multiply. 5 times 4 times 3 times 2 times 1, and calculator will do that really, really quickly. It's 120 different orderings. 120 different orderings. Gosh, that's a lot of choices. I don't want to write that out though every time. So there's this, I have what I call my silly sayings in my math classes, and mostly they help students to remember stuff. And most of them are kind of silly. So one of my silly sayings, for example, is if you're solving an equation, and you remember on solving equations, right, you want to add the same quantity to both sides or subtract from both sides, or maybe you'll multiply both sides or divide both sides. And my silly saying is, we do to the left, do to the right. Whatever you do to the right, do to the left. And I have things like that that I say. And I call them my silly sayings. So one of my silly sayings is, I started off, I say, among all the tribes of humankind, mathematicians are the, and the first time I do it, I always let the kids fill in the blank, right? Among all the tribes of humankind, mathematicians are the, and people say smartest, and okay, that always makes me feel good because I'm a mathematician, so they're the, and whatever. Most boring, yeah, right, thanks. It's the truth that hurts. No, the way I end this silly saying is, among all the tribes of humankind, mathematicians are the laziest. And the reason I say that, well, for one thing, it's introspection. I look at myself and I know how lazy I am. But I also look at mathematical notation. And so I mentioned this as something that might help some of you in the future. Not all of my students, and I have a lot of students, and some of them are students in math classes. Most of my classes outside of this one are math classes, but I've taught other things in the past too. Most of my students aren't really good at math when they walk in the door. And one of the reasons they get confused by math is, well, there's all this weird notation, right? And you've heard the old joke, I liked math before they brought the letters in. Yeah, if someone says, what's 3 times 5? You say 15. That was kind of fun. Well, now solve 5x plus y equals 12. And you think, the letters, what? And so people, they don't like the notation. And so when I make this joke about mathematicians being lazy, what I want you to notice is every time there's a weird, new, complicated, confusing notation, It's because they're trying to avoid writing something that takes too long. And so here, instead of writing 5 times 4 times 3 times 2 times 1, what a mathematician would write is they would write 5 with an exclamation mark. And this isn't 5, right? Because there's an exclamation mark. Yeah, that's the joke I make. See, this is 5, and this is 5 because there's an exclamation mark. No, this is pronounced 5 factorial. So the exclamation mark is this factorial operator. And why does it have to be something new and something different? Because it's better than writing times 4 times 3 times 2 times 1. You can just put the exclamation mark. And you think, well, that's not so bad. What's the big deal? I mean, how lazy are these mathematicians? Let me tell you, they're really, really lazy. But in practical terms, 10 factorial is really easy to write. Let me do it up here in the 10 factorial, just as another example. What is this? Well, this is 10 times 9 times 8 times, and I'm not enjoying this because I'm a mathematician, and I'm lazy, and this is taking too long, and it's like, what? And then what? You'd use a calculator, and you'd say something like that. Wow, oh, Gary, yeah, I have a mnemonic. Yeah, it uses the number system, the phonetic major system that you learned uh, in Harry Lorraine's book. And so, yeah, I know that one. It's the only one I have to use that for because it's big enough. The first 10 or so, I kind of know why, because I took a course in combinatorics when I was about your age, maybe a couple of years older. And I used a lot of these factorials. And so if you say, what's 7 factorial? I say 5040. And I don't need a mnemonic because I just know it. I've used it. And this one I have to use a mnemonic, and it always takes me a second. Hint 362 machine. There you go, right? MJ ch sound N2 machine. And then figure out what I did for the rest. Anyway, there's the idea of factorial. And so this, our first principle was this fundamental principle. Our second principle we'll call the factorial rule, and we'll write it down